Hi guys, how you going? My name's Ben Hardless. Welcome to the ENM2600 playlist. Last time we talked about Euler's formula and we had a bit of a dive into that, and I just want to take that idea a little bit further today. I can't say the name properly, so I'm just going to write it and you decide for yourself how to pronounce it, okay? How to say that? I have no idea. Okay. So really, this leads on from what we discussed last time. And if you recall, last time we said that if we have some complex number, z, that is expressed as some magnitude of z times cosine of theta plus j sine of theta. And, you know, if we say, for our purposes today, let r equal the magnitude of z, so then we can say, well, z is equal to r cosine of theta plus j sine theta. So I think this was a couple of videos ago actually, and then we said this is equal to r times e to the power of j theta, right? These things are absolutely equal. We didn't rigorously prove it, however, we did hopefully give you a bit of intuition for why this is. Now, what we want to talk about today is just taking this idea a little bit further and look at what happens when we raise complex numbers to different powers. And I think we talked about that last time a little bit, where we did things like, and I'll just make a little line here so we know that we're talking about something different. If we, for example, in z is the same z that's over there on this z over here, this z over here, same thing, right, is equal to all of this stuff over here. But what happens if we raise z to, say, the second power, z squared? What do we have then? And you know, we discussed, I believe, that was the same as doing this, which was the same as doing this, right? And this is like index rules, so you just everything that's multiplied inside the brackets, you just this is the same as r to the 1, really. So you multiply this exponent by 2, and you multiply this e to the j theta, you multiply that exponent by 2, and we're going to get j 2 theta, right? Now, in a general sense, we could say that z to the power of n is equal to r to the power of n times e j n theta. So hopefully that's making a lot of sense to you, all of this business over here. We've got a specific example that's quite simple, really, and then we extended that rule to be telling us this: r to the power of n times cosine n theta plus j sine n theta. Let's take this idea a little bit further. What if we have, if magnitude of z is equal to 1, then z to the 1, if we go by our rule that we've sort of created over here, then z to the power of 1, if we follow that through, that will be equal to r, right, which should just be 1, because its magnitude of z is equal to 1, so that's this guy. R is the magnitude of z, right? We've said that just here, so we've got 1, so we don't need to write it down, times cosine of theta plus j sine theta. Now, if we make this an n, right? If magnitude of z is equal to 1, and instead of a 1 here we put an n, so we're not raising it to the first power, we're raising it to the nth power, then if you look over here closely at what we've done, then this is going to work just fine. Right? Where's the r? That's what I would be thinking if I'd never seen this before. Where is the r? You had an r here, Benny. Where's the r this time? Well, remember, the r is just the magnitude of z. So in this case, this r term is just 1. So it's 1 times all of this, if you like, right? So we don't really need to write the r. That's all I'm saying. This is only if magnitude of z is equal to 1. So hopefully I've satisfied you that you don't need to freak out about the missing r. Now, what happens if we have z to the negative n? What happens then? What's this going to be equal to? Well, know that cosine of alpha is equal to cosine of negative alpha. So I will not explain why that is true. However, hopefully, if you've done a bit of trig before, you will know that that is true and you will believe me. So that means that, okay, we'll follow our little rule over here, and this is going to be cosine of negative n theta plus j sine negative n theta. Now, what is going on over here? Well, hopefully you also know that sine of negative beta, I'm just choosing beta so it's a different variable than in the alpha term, is equal to negative sine of beta. So if we now apply these little trig rules that we know over to our problem, then we can say that z to the power of negative n will be cosine of n theta, because it's negative of something, and we've already said if you've got cosine of something, that's the same as cosine of negative of that something. They're exactly equal. So we can just get rid of this minus sign and it's perfectly legit. And then, okay, we've got sine of negative something. So we explored that with this rule over here with the sine of negative beta, and so we've got negative of something inside, sine of negative something. So we can just take the negative outside, right? So isn't that the same as we take the negative out and we have this? And absolutely it is. So, you know, the important ones here to know are really this one, which is, I'm going to put a little box around it, right? This guy and this guy. So what can you do knowing those things? Well, what we can do knowing those things is we can say that, all right, well, what happens then if we do z to the n plus z to the n? Oh, that's an interesting idea. Let's try that. Well, you can see there's a cosine n theta here and there's a cosine n theta here. So if we add these two things in the yellow boxes together, aren't we going to get, we're definitely going to get 2 cosine n theta, because we've got one of them, we're adding it to this one, there's another one, it's positive, cool, 2 cosine n theta, sweet. And then we've got a plus j sine n theta, so we've got j sine n theta plus negative j sine n theta. So we got this thing plus the negative of that thing, so it's going to cancel out, right? So it's going to be 0. So here we go. This is interesting. And what else have we got? We've got another thing. Another thing we can do if we do z to the n, oh, sorry, this is meant to be negative n over here, my apologies. Z to the n minus z to the negative n is equal to what? Well, interesting. If we apply the same rationale, so this top one minus this bottom one this time, because we're subtracting, cosine n theta minus cosine n theta is 0. J sine n theta minus negative j sine n theta, well, minus and negative is plus, so it's going to be j 2 sine n theta, right? If we have a think about it, let me give you an example of how this might be useful. So if I said to you, what if I wanted to express sine squared of theta? So I've got sine squared of theta. I want to express that in terms of sines and cosines. I don't want this as, you know, a trig function raised to an exponent. What do? I don't want that this sine squared. I'd rather have, you know, just a sine or just a cosine or something else. Anyway, this is a really common one. So, okay, well, let's just pause for a minute and say dot 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 dot, and we'll have a think. And so, what do we know? We know if we take z to the n minus z to the negative n, we get j2 sine n theta, right? Interesting. And if we make these ones, so instead of n's, we'll say they're ones, right? Minus 1. Then there's this n is gone away, right? So 1 theta, cool, because n is equal to 1. All right, now we're getting somewhere. So we know this just based on what we did before. So how can we apply that? Well, if we then come down here, so we know this thing over here, z minus z inverted, or z to the negative 1, is equal to j2 sine theta, or 2j sine theta, or 2 sine theta j. However you want to say it, it's the same thing. So what happens if we then square that? Right? So we say, well, j2 sine theta, and we just square that bad boy. What happens then? Well, okay, we've got to square both sides of the equation, so we'll take our previous equation, right? This, and we will square it, and then we'll work on it. Let's scroll down a bit. Okay, so left side. I'll do it on a separate line so you can see it. It'll be the same thing as j squared times 2 squared times sine squared theta, right? Is equal to, what's this going to be? Now, hopefully you know that if you have a plus b, or a minus b in this case, right? A minus b, and you square it, that will be equal to a squared plus b squared minus 2ab. So we'll just, imagine this is the a and this is the b, we'll just do that. Right, okay. So this thing squared will be z squared plus z to the negative 2, right? So z to the negative 1, we square that, it'll be negative 2, minus 2 z to the 1, z to the negative 1, and because they're the same base, we can simply add the exponents, which 1 plus negative 1 is 0. So this all evaluates to z to the 0, and z to the 0, just like anything to the 0, exponent 0 is equal to 1. So we can just get rid of that guy, right? In fact, I'll leave it there so in case you're looking at it later and you want to retrace the steps. All right, cool. So, all right, let's work on this left side. J squared. What's j squared? Well, remember, j is equal to square root of negative 1. Therefore, j squared is equal to negative 1. So this becomes negative 1. 2 squared is 4, right? Times 4 times sine squared theta. And now we're getting somewhere because we actually have a sine squared theta term here. So we knew that if we had this j2 sine theta up here on the top right, if we had this j2 sine theta, we figured, oh well, if we just square that, we'll get closer because we'll have a sine squared theta, right? Now we're actually there. So we'll just keep going. Z squared plus z to the negative 2 minus 2. Let's just tidy this up. We can get rid of this negative 1 and just say, well, negative 4, right? Okay. Now what can we do with this z squared and this z to the negative 2? Well, remember, if we scroll back up, yeah, so sorry, I was waving the mouse around, but you probably couldn't see the cursor. Anyway, this z squared and this z to the negative 2, what are we going to do with it? Well, let's scroll back up and have a look at these rules over here. What we're doing is we're adding them up, aren't we? So z to the n plus z to the negative n equals 2 cosine n theta. So, right, what we're doing, this is very special. We're going to take this and we are going to substitute it for this. This guy is going in there. So we're going to take this 2 cosine n theta, and where the n in this case is equal to 2, we're going to plug it in over here. And what does that give us? Well, that gives us, we can write this out again, negative 4 sine squared theta is equal to 2 cosine 2 theta minus 2, right? So the minus 2 is still there. All we've done is apply the rule that we discovered earlier. Now we're really somewhere, right? Because we've got this expression. We can actually do something with this. So how do we get rid of this negative 4? Well, one thing we can do is we can divide both sides by negative 4, right? And if you do that on the right hand side, that's just like doing it with both terms individually, isn't it? Yeah? So you can divide the whole thing by negative 4. You can do it by individual terms. Same thing. So what are we going to get? This is going to give us, if we look at on the left side here, the negative 4 divided by negative 4, that will cancel out. So we'll get sine squared of theta equals, and then what's it going to do on this right hand side over here? Well, minus 2 over 4. Well, I'll put the minus over here just so it's very clear that we're doing minus 2 over negative 4, right? So, well, when the negative is on the denominator here, that's okay, because we could just move it to there. That's the same thing, right? Like 1 over negative 1 is equal to negative 1 over 1, right? So all I've done is I've taken the negative from the bottom where this 4 is, and I've put it up top, and now we've got a negative minus, if you think about it. So that is gonna simplify to a plus. Okay, so we've got 2 over 4, and what about here? We've got 2 over negative 4, right? Because because of our order of operation, we've got 2 times cosine 2 theta, and we could divide the whole thing by negative 4, or we can do 2 divided by negative 4 times cosine 2 theta. That's fine. Same thing. Anyway, so we can do the same thing over here. We put the minus up the top, and this is negative 2 over 4, or negative a half, but we'll simplify it afterwards. Negative 2 over 4 cosine 2 theta. So, and this is the positive one, so plus 2 over 4. So we've put that first, and then we're going to say minus, right? That's this minus right here. 2 over 4 cosine 2 theta. Okay, and I'll get rid of this. I think I made that point. Very interesting. What else can we do? We could probably factor out a half. We can change that to a half because it's equal to a half. We can change that to a half, and then both of these terms have a half in it, so we can factor out the half. So what we're going to get is sine squared of theta is equal to 1/2 times 1, right? That'll give you this bit, minus cosine of 2 theta. All right, so this is really pretty cool because we've been able to derive this, and I appreciate it took a long time because you're just seeing it for the first time and I'm explaining it right now. However, when you're used to doing this, it's actually quite a quick process to do because you already know all of the steps and you're not having to go through it mandrolically like I've just done. Anyway, hopefully you found that interesting, and perhaps I'll do another video on this a bit later. Thank you for your time.